So, today's discussion is on tolerance design. First of all, let us know what is tolerance. Tolerance is permissible deviation from specified value or a standard. Like fabric width, the nominal value could be 1 meter, and then the tolerance which could be given is, let us say, plus 2 centimeter or plus minus 1 centimeter. So, we can have a tolerance like this here, plus minus 2 centimeter or 1 centimeter. Similarly, for fabric GSM it could be 200 gram plus minus 5%, or yarn RKM could be 16 centinewton per tex plus minus 1 centinewton. So, the tolerance part could be in the same unit or could be sometimes given in percentage terms also. So, whenever specifications are given, tolerance also needs to be given, because it is otherwise impossible to make a fabric which is exactly 1 meter, which will not be possible, or a fabric GSM which is exactly 200 gram, because the process will have its own variations. There are a lot of reasons why the variation comes, and we always try to minimize the variation, but depending upon the capability of the process and the variability that exists in the raw material, there will be always some deviation from the nominal value that we expect in a given parameter. But tolerance are always it may be suggested by a buyer and or by a customer, and the producer has to produce goods which will meet the tolerance. So, we will discuss about the designing of tolerance. So, purpose of tolerance design is assignment of tolerance to parts, to assemblies or to processes. If we have to meet the tolerance of the final product may have many parts, and therefore, what will be the tolerances of those individual parts. Like a product may consist of a few fabrics, that could be inner layer, outer layer, that could be middle layer, that could be hood. So, these are different parts of the fabrics, and if somebody says that the nominal weight of this uniform or this jacket, whatever it is so much, some value x, with a tolerance of 4%, 5%, 1%, whatever it is, then when we are trying to manufacture that product, it consists of so many different components, and we have to also now see how much tolerance we should give to those individual parts or components that will contribute to the weight, total weight of that garment. It could be uniform, it could be jacket, whatever it is. So, based on the overall tolerable variations in functional requirements. So, if I say functional requirement is the weight, that is weight becomes very important in certain cases, then the functional requirement becomes weight, and that could be tolerance that will be given to the total weight of it. So, what will be the weight of individual components, parts? That is how to design that. As we have given an example here, that a required weight of a winter jacket is 800 gram plus minus 50 gram. What will be the weight and tolerances of inner layer fabric, insulation layer, outer layer, hoods, zippers, because all of them, weight of all those individual items is going to contribute towards the total weight of the winter jacket. So, it could be weight, it could be any other property, maybe insulation property, or it could be the size, whatever it is. It could be in some cases the strength, some cases it could be air permeability, whatever it is. We need to find out the tolerances of individual components, which is contributing to the overall tolerances of the product as a whole. Now, tolerance have different meanings at different stages of design process. First one is customer tolerance. Customer may have explicit or implicit requirements and allowable requirements variation ranges. So, the customer may specify okay, this is what the tolerance he is going to accept, beyond which he will not going to accept. If I say the count of a yarn and I say I want to buy 10 tons of cotton yarn from a particular factory, and we specify that the cotton yarn count should be 20s NE, and they can give a tolerance that 20s NE plus minus 1 NE. So, that is the tolerance that is given, that is if it is as long as it lies the any test that we perform on it and we get a value which is varying between 19 to 21, it will be acceptable to me. So, that is what is the tolerance given by the customer, and the manufacturer has to meet this tolerance given by the customers. So, he has to design the process so that he can meet it. So, customer tolerance is generally given by the customers. Functional requirement tolerance, customer tolerances are to be mapped into design, functional requirements and functional tolerances. So, customer tolerances has to be mapped to actually what is the functional requirements. Customer may say this fabric should last for 2 years at least. Now, when you say it lasts for 2 years, that is the customer statement. We have to now map it to the property of the fabric that contributes to the life of a fabric, depending upon where the fabric is going to be used and what are the factors which will be responsible in damaging the life of the fabric. So, keeping in mind those things, we have to decide that what fabric properties, that is basic property of the fabric that affects the durability, which could be strength of the fabric, it could be the UV resistance, it could be the abrasion resistance, like that we have to relate. And then we have to find out that what are the tolerances of these properties that we should have when I am trying to design, so that I can meet the customer tolerances. So, functional tolerances has to be derived from the requirement of the customer. Design parameter tolerances, to deliver functional requirements with tolerance, the design parameters must be set at correct nominal value. Their variation must be within the design parameter tolerances. So, design parameter that we finally have, those parameters what should be the nominal value and how much tolerance we should give to it, that is the design parameter tolerance. Like say strength of a fabric we know depend upon the ends and peaks per inch. So, what should be the exact tolerances in ends and peaks per inch? That ends and peaks per inch become my design parameter. With that I can vary the strength requirement of the fabric in both warp and wave directions, and therefore, they become my design parameters. The count of the yarn becomes my design parameter. So, we need to know what are the nominal value of this design parameter, that means target value that we should try to achieve, and how much tolerances we should have there. Now, tolerance development process. Here is a diagram which is representing the development process. One is, the first one is customer attribute and customer tolerances that we need to know. What the customer is looking for. A customer not necessarily a person who has a technical background. So, he may not be able to, or he or she may not be able to always specify the requirements in scientific language. So, customer statements which may not be very scientific in nature needs to be translated into a scientific statement that will satisfy the requirement of the customer. So, customer attribute or customer tolerances, from there we must go to the next step, that is functional requirements and also tolerances of that. Then comes the design parameter requirements, as we have already stated earlier. So, once we have the functional requirements and their tolerances, we can go to the next step, that is design parameter requirements and their tolerances also. After that, what comes is manufacturing process variable and their tolerances. That what is the, ultimately I have to manufacture the product and give it to the customer. So, after doing the necessary calculation to find out what are the design parameters, now I have to set the machines which is manufacturing the product, so that I can really satisfy the requirement of the customers. So, that setting of the machine parameters, which could be speeds and which could be the any other machine parameters that one can think of, all of them needs to be properly set on the machines, and other whatever parameters are there while I am trying to manufacture a product. Speed is maybe one of them. Other than we may have some other parameters, settings of different organs of the machines. So, there also we need to know what is those manufacturing process variables which are there and how much tolerance we should have, so that the process does not go out of control and keep producing something which is not going to meet the requirement of the customer. So, stages of development is stated here: functional tolerance. From there we go to the system and subsystem tolerance. Then comes component tolerance and process variable tolerance. So, first we look into the functional tolerances, and followed by it we look for system and subsystem tolerances in a product, because a product can be also, now I have already discussed it earlier, that a product sometimes may have many subsystem within it. It all depends upon the type of product, and therefore, functional tolerances and system and subsystem tolerances need to be found out. Then will come the component tolerances are determined, and finally, the process variable tolerances are to be determined. So, this is a in the development process, these are the stages: functional tolerance, from there we will go to system and subsystem tolerance, then we will go to the various component that you use to manufacture that product. Each and every component, what will be the value, what will be the every component has a purpose, and therefore, keeping in mind that purpose, what sort of values we expect which will satisfy the requirement, that we need to find out, and how much tolerance to be given to that. So, tolerant design involves determination of design parameter tolerances and basically process variable tolerance. These are the two main activity, that is design parameters and process variable and their tolerance. This is what will be most important part in the development of tolerance. So, in the tolerance design, see there is a high level requirement and tolerance, and there is a low level requirement and tolerance. Low level requirement means the property, it is there basically independent variable that affects a dependent variable, that is that depends upon these independent parameters. Let us say as an example, if I say that if the higher level requirement is the strength of a fabric, then the lower level requirement will be strength of the individual yarns. Then another thing could be ends density and peak density. The third thing could be the type of weave, whether it is a plain weave or a satin weave or a twill weave. So, they becomes my low level requirements. So, high level requirement depends upon the low level requirements. So, therefore, we can write that y is a function of x 1, x 2 up to x n, and these are the basically independent parameters that is going to affect the dependent variable, which is y. So, as an example, I have taken y as a fabric strength, and x s could be, as I said, count of yarn, tenacity of yarn, ends and density of yarn, peak density of yarn, type of weave, you can keep adding them. So, the relationship between these stages is known as a transfer function between higher and lower level parameters. Whatever is the form of relationship, sometimes some relationship may be available, because from the research literature we can find it out that how y and x s are related to each other, or sometimes we need to do some experiments to find out what is the exact relationship. And there what comes into the picture, that when you want to develop a relationship between dependent and independent variable, then we take the help of design of experiments. In the design of experiments, we will be able to establish a relationship based on multiple regression. What sort of relationship exists between these variables, dependent and independent. So, assume that this is my transfer function. So, the main task is, given the target requirement of y and its tolerance, if both of them are given, that the fabric strength should be, let us say 1.5 kg force. and the tolerance is plus minus 0.2 kg force. So, tolerance is also given and the target value has been given. We need to find out what should be the tolerances of exercise and what should be not only tolerance, this is one thing, what is the should be the target value of excess also. Both of them, especially here we are discussing about tolerance. So, therefore, we are focusing more on tolerance. So, if the tolerance of the output is given to us, how do I find out tolerance of the individual independent parameter that affects the output parameter? So, the aspects of tolerant designs are, one is to manage variability. If the tolerance is tight, if we narrow down the tolerance, then we have to have a very strict control on the process. So, any reasons of variability, anything that can affect variability, all those factors needs to be under proper check, because when you study variability in the properties of a product, then we can also find out why this variability exists. What is the role of the process on the variability, what is the role of raw material on the variability, or what is the how the process might get disturbed. So, there are many factors which can affect variability, some of them can be under control and some variabilities also remain uncontrollable. That is something where we have no control on them. So, it happens. So, but variability control becomes very important in tolerance design, understanding the source of variability and how to control them. Achieve functional requirements satisfactorily and keep design cost low. So, that is also another objective, that the design cost should be low, that is we should not finally attempt for tolerances which are difficult to achieve, and if we try it, cost might go high. So, keeping in mind the cost also, we have to see already you must be knowing that there are some textile mills are there who can maintain the count of yarn within a very narrow limit with 5% worsted. At the same time, there are also textile mills which will keep it the count variability which will fall into 10% of the worsted value. That means, a mill which is producing a yarn, the nominal count may be still same, but the variability in one mill will come Worcester standard of 10%, the other one is coming at 5%. So, why the difference is there? So, difference must be because of the processes in the two cases are not under proper. In the one case it is highly controlled process, in the other case it is not at all controlled, and therefore, the differences are observed. And the moment we want to go for, we narrow down the tolerance, the cost is going to be more and more, because you have to have proper process controls, you may need to have more and more sensors, you need to have better machines. So, obviously, cost will go high. So, keeping in mind the cost part also, we have to decide whether it is achievable or not. Now, worst case tolerance. This design is based on worst case scenario. Let y be a function of x 1, x 2, x 3, x n, where x 1, x 2, x 3, x n, these are basically lower level parameters, and y is basically higher level parameter. That means, y depends upon x 1, x 2, x 3, x n. Let the target value of y is t y and the tolerance limit of y is delta 0. So, y is within the specification if y remains within these limits t y plus delta 0 and t y minus delta 0. Then we say that it is within the specification limit. But at times the tolerance limit may be asymmetric also, this can also happen. That is, we may have a situation where it is like this side right hand side t y plus delta 0, right hand side t y minus delta dash 0. So, the two sides, the two limits of the tolerance on the right hand side and left hand side may not be exactly same, it may not be plus minus 2, it could be plus 2 minus 1, that kind of, like we want to make a fabric and say I want a fabric of 1 meter, but I can tolerate if the fabric becomes shorter by 5 centimeter, but I can tolerate if it is fabric width is longer by let us say 1 centimeter. So, 1 centimeter more than the nominal value is acceptable to me, but on the lower side it should not be 1 centimeter less, it should be just 0.5 centimeter less. So, this is what is called asymmetric tolerance, and in many situations it could be like this, and it could be also that could be some situations where that could be tolerance only on the lower side or only on the upper side, that we can have only upper tolerance or lower tolerance. As an example, let us say I want, a company says or a customer says we want a yarn of RKM 18 centinewton per tex, but I can accept if it is coming within up to 17. So, I am ready to accept if it falls down from 18 to 17, that is 1 centinewton per tex, but the upper limit I do not keep. If you give me 19, 20, 21, I do not, it does not matter to me, I will be happy. So, there are situations where there could be only upper limit or could be only lower limit. Similarly, like let us say if I say I need a uniformity level of a yarn, as an example, it could be for that matter any other thing where the value should be let us say Worcester percentage 13. So, if it is up to 14 I am accepting it, but the lower level I do not keep anything, there is no limit. That is, if you give me from 13 to 12 or 11, 10 I will be happy, because lower it is uniform it will be the. So, that side I do not keep any limit, on the upper side I keep a limit. So, there are situations where that could be limit only on one side and not on the either upper or lower. This could be there in many situations, or they could be equal from the nominal value, or they may be asymmetric also. All sort of things might be there in the tolerance. So, the target value of x I is T I and the tolerance limit of x I is delta I, and x I is within specification when x I remains in this range. X I is T I minus delta I greater than or less than T I plus delta I. So, worst case tolerance design rule is that T y minus delta dash 0 should be the minimum of this function f x 1, x 2, x 3, x y up to x n, where each x I has is within this limit t plus delta I, and this should be not plus, this should be minus. Or it could be t plus delta 0, which is maximum of these values. Now, let us take an example. Let us say target and tolerance of a stack of fabrics. So, we have a, let us say, stack of fabrics placed one on the top of the other, and each individual fabric is having a thickness x I, and it is a stack consisting of, let us say, maybe 10 fabric layers, and the total thickness is y. In the garment industry, fabrics are laid one on the top of the other, then they are cut together. So, the total thickness is going to be x 1 plus x 2 x I up to x 10, because we say I is varying from 1 to 10, that is there are 10 layers of fabrics. Let the target value of small x I equal to T I, and the tolerance of small x I is equal to delta I. So, this is the target value representing T I, and the tolerance is represented by delta I. So, let the target value of y, that is the output total, is T y, and tolerance is delta 0. So, this is for x I, and this is for y, and y is a function of x. So, y is a simple function of x in this case, because y is going to be sum of the individual layers. So, y is basically this x 1 plus x 2 up to 10 layer. So, T y, the target value of y will be T 1 plus T 2 up T I up to T 10, because these are the target values of x i's. So, T I plus delta 0, if we want the relationship between high and low level tolerances, is maximum x 1, x 2, x 3 and up to x 10. So, this is going to be T 1 plus delta 1, T 1 plus delta 2, T I plus delta I, T 10 up to delta 10, and therefore, I can write all T is one side and all tolerances together. So, therefore, similarly for the lower level, no sorry, this is the T y plus delta 0, that is the target value of y plus its tolerance, and target value of y subtracting the tolerance, that this is the tolerance in which the T y is going to lie. So, T y minus delta 0 is going to be the minimum of this, and therefore, it is going to be like this. Minimum value basically means it will be T 1 minus delta 1, it will be T 2 minus delta 2, this one will be T I minus delta I, T 10 minus delta 10, and then what we do, we club together all T's on one side and all delta also we club them together, and therefore, we are getting, therefore, delta 0 becomes a sum of this delta 1 plus delta 2 plus delta 3 delta I up to delta 10. That means, the tolerance of the T y, which is this total thickness of the fabric, is going to be the sum total of tolerances of individual fabrics. So, this is how, where it's, see where is minimum, if I write this line here, it is basically T 1 minus delta 1 plus T 2 minus delta 2 plus we are going like this and going up to then T 10 minus delta 10. This is what we have done. This line is missing here. Next line that put will be that is put all the T's together and all the deltas together. This is the situation, and therefore, we can write that delta 0 this is going to be sum of this or sum of this. So, the tolerance of the stack is going to be sum of individual tolerances of the fabrics. Now, if I take a real example of this, let us say the nominal thickness of a fabric is 0.2 mm. All the fabrics assumed to be they are of same fabric pieces. So, all of them have nominal thickness 0.2 and tolerance is 0.02. That means, there are some fabrics where the thickness will be 0.2 minus 0.2. That is, in some cases the T y could be difference between these two, and that is going to be 0.18 mm. And there are some fabrics where it could be the other extreme could be 0.2 plus 0.02, and it could be 0.22. That is what basically it means. That means, I have 10 fabric layers, but the fabric layers all of them their nominal value is 0.2, but the tolerance has been given which is 0.02 mm. That means, in the worst case I will have some fabrics of 0.18 mm, and in other worst case that all the fabrics are thicker and they may be therefore total each fabrics may be 0.22 mm. These two are the two different extreme scenarios. So, the tolerance limit for the pile of fabrics is going to be sum of the individual tolerances. So, therefore, it will be 0.02, 0.02 all of them are same in this case. So, there are 10 fabrics, so 10 into 0.02 it is going to be 0.2 mm. So, for this stack of fabrics the tolerance is going to be 0.2 mm and the nominal is going to be 0.2 into 10 that is 2 mm. So, T y will be 2 mm, 0.2 into 10 that is 2 mm, and delta 0 is going to be 0.2 mm for the stack. This is what we will get. So, we will know because this is what the value we will get. The most of the time we will be interested in the reverse, that is given this the stack should be of 2 mm thickness, because my machine setting is permissible. That machine maybe cutting machine can only handle a fabric of 2 mm thickness. Just as an example I am giving it, maybe they can handle actually much more, but obviously there is a range in which it will be able to operate. Up to this thickness it will be able to operate. If I try to go beyond that, the machine will fail, it will not be able to cut the fabrics. So, such kinds of situation could be there. Here for as a simple example we are giving like this, that the values could be 2 mm, 0.2 mm. Many times we need to know the reverse way, as I said, that if this is given to me and its tolerance is given to me, what will be the individual fabric thickness and what should be the tolerance of the individual fabrics. The another example is this. What is this? Two folded fabrics are to be put inside a packet. From the given data, calculate target dimensions and tolerance of the packet C. So, therefore, let us say as it yes, this diagram I am looking for. So, let us say I have two fabric pieces and they are in folded state, one is A, the other one is B, and I have to now design a packet within which these two fabrics will be inserted. And obviously, the packet has to be such that this, if it is too short, it will be very difficult to put the fabric inside the packet. If it is too large, then also within the packet the fabric will move. So, in the packet that we are going to design, it should have certain nominal value we should know, and how much tolerance has to be given to it. So, that neither we have difficulty in placing these two folded fabrics inside the packet, and not the fabric is going to move too much within the packet. It is as an example we are giving. So, in this case, target value of the tolerance of A is given 20 plus minus 1 centimeter, and the target value of tolerance of B is given 10 plus minus 1 centimeter. Clearance that we require here has to be within this range 1 to 6 centimeter. So, how to go about it? What should be the target value of C and what would be the tolerance? Now, the solution is that the target of C minus delta dash 0 is going to be 1, and because this is 1 centimeter, and therefore, 1 is going to be minimum of C minus A minus B. See, y is what? The clearance is y is C minus A minus B. Actually, C is A plus B plus y, where y is the clearance. So, y is C minus A minus B. So, if the tolerance minimum value is 1, is minimum C minus A minus B. So, this is going to be T C minus delta dash C plus 20 plus 1 plus 10 plus 1, that is we are considering them to be maximum value. If we consider, then this is going to be T C minus delta C minus 21 minus 11, that is going to be equal to 1. And the other one is that T plus delta 0 is going to be 6. So, 6 is going to be maximum of C minus A minus B, that is the upper limit we are putting it. Therefore, it is going to be T C plus delta C minus 20 minus 1 and 10 minus 1. The clearance will be maximum only when these two folded fabrics are minimum. So, 20 minus 1 and 10 minus 1, and therefore, it become T C plus delta C minus 19 minus 9, that becomes my equation 2, and we get two equation, that is T C minus delta dash C. Delta dash C is the lower side of the limit, is going to be therefore 33, and T C plus delta C is going to be 34. You have to add them, 6 plus 19 plus 9, 1 plus 21 plus 11. From there, if we assume symmetric tolerance limit, that delta dash C and delta C are same, in that case we can now solve these equations, two equations, to find out what should be my T C value and what should be my tolerance. That is, if I want to know T C, since they are same, we simply add these two, 33 plus 34 divided by 2, that will give you T C 33.5 centimeter, and delta dash C, similarly we can work it out, it will give you 0.5 centimeter. So, that means the C has to be designed in such a way that its target width has to be 33.5 centimeter and with the tolerance of 0.5 centimeter. That is how we must manufacture the packet, that is C this case. The other thing that we will decide now is the statistical tolerance. The objective is to ensure that the high level requirements meet its specification with high probability, and low level characteristics are considered to be independent random variable as they are made in different unrelated manufacturing process. The different components are made in different manufacturing process by different machines, it could be, and therefore, they can be all considered to be independent random variables. So, low level characteristics, that is xi's, we assume them to follow normal distributions, that is the safest way, and most of the time that is what we assume, and we then move forward. So, xi's are following normal distribution with mean mu I and standard deviations sigma I. High level requirements is also normally distributed with y's, that means are normally distributed with a mean mu as standard deviation sigma. So, total variance and process capability also we need to now little bit of understand. We said, see, process capability is judged in terms of this parameter called Cp. Capability of the process. How it is judged? USL minus LSL divided by 6 sigma, that is USL and LSL are upper and lower specification limits that has been provided by the customer, that these are the specification limit, and we must get the the product within these two limits. It could be anything for that matter, maybe dimensions could be, or it could be weight, it could be anything, any parameter they can say this is the limit, and the process variability which is sigma 6 times sigma, if we divide this, then the value that we get, this is what is known as process capability. If the process is centered, that is target value and mean of the characteristics are same, then Cp can be also written as USL minus Ti by 3 sigma or Ti minus LSL by 3 sigma. Process is centered, that is target value and mean of a characteristics are exactly same. That situation, the Cp which is USL minus LSL by 6 sigma, it can be also USL minus Ti, or Ti, what is Ti? Ti is the target value of Xi. Xi is the target, one parameter is Xi, its target value is Ti. So, USL minus Ti by 3 sigma, that will be should be equal to other way Ti minus lower specification limit by 3 sigma, and the difference between these two is what the tolerance is all about, delta I. So, it becomes delta I by 3 sigma I for ith parameters or ith lower level parameter. So, Cp is delta I by 3 sigma I. If Cp is delta I by 3 sigma I, therefore, delta I is going to be 3 Cp into sigma I for each low level characteristics Xi. That means, the tolerance of a lower level characteristics which is excise, tolerance of that is connected to the Cp value of the process, that is capability of the process. Can the process really capable to give me so much tolerance or not? If somebody claims, somebody says that I can give away, suppose I am saying suppose a machine generally produces a non-woven fabric where the Cv has been found to be around, let us say, take a value, arbitrary value, let us say 10%. So, we know that this whatever we do, this particular non-woven machine always give me a Cv of 10%. If I know the Cv of 10%, we can find out what is the standard deviation also. Now, therefore, if somebody, that means the process is capable to produce that much only. If I demand a value of 5%, then the process will not be able to give me. So, if my customer asks that I need a product where the Cv will be 5%, and if I know that my process can only give at the most 10%, therefore, we should say that the process is not capable. There is no point in taking that order and trying to execute it, because we will fail because process is not capable. So, we must understand what is the capability of a process. If it is spinning process, weaving process or garment manufacturing process, whatever process it is, we must have idea the capability of the process. So, this is the relationship between the process capability Cp, the standard deviation and the tolerance. For high level requirements, similarly, we can write delta 0 is going to be 3 into Cp multiplied by the standard deviations. Cp and standard deviation. So, Cp value is the process capability value. Actually, this is a part of 6 sigma. So, when Cp is 1, we say it is 3 sigma level, and this is the corresponding diagram, that is, you see, if this is the process variability, then the lower specification limit and upper specification limit are lying at these 2 points, and these 2 points, the distance between these two in terms of sigma scale is exactly 6 sigma. When the distance between, that is difference between LSL minus USL divided by 6 sigma equal to 1, then we say it is Cp value is 1, but sigma value is 3 sigma. Similarly, the next one is 4 sigma. In the case of 1 Cp value 1, 3 sigma level, 0.27% of the product will be outside the specification level. That basically means 0.27%, roughly 0.3%. If I get the process Cp value 1, if it is 1.33, which is equivalent to 4 sigma, 0.0064% is outside the specification limit. Cp 1.67 and Cp 6 sigma level is this one. Specification limits and the, you see the limit 3 sigma limits of this, they are far away. So, specification width is much more, and the 3 sigma width of the process is much narrower, and therefore, in these situations hardly any defective material will be produced. That will go beyond the specification limit, because specification limits are so wide in this case in comparison to the process. So, this is the relationship between Cp and sigmas are stated here. like this. So, Cp2 is something very low defects that will be produced, which is almost difficult to achieve, but many high end industries are trying to achieve this value. In our case, even a Cp value of 1 itself is something very good, but usually it would be sometimes Cp may go below 1, it could be 0.8, 0.6, 0.7. So, that we produce actually more defective materials, something which will go beyond the specification limit. Anyway, that needs a detailed discussion on 6 sigma, that we have some understanding of 6 sigma should be important here. Now, we are going for this linear statistical tolerance, that is, if y is a function of x 1, x 2, x 3 and x n, and let us say that function is stated like this, a linear function, that is y equal to a 1 x 1, a 1 x 2, a 2 x 2, sorry, this will be a 2 x 2. In that case, the variance of y will going to be a 1 square sigma 1 squared, a 2 square sigma 2 squared, a I square sigma I squared, a n square sigma n squared. This formula is important to know in the case of linear statistical tolerance. That is, we are assuming a linear relationship between y and x, but many a times it could be nonlinear. So, that will be also that can be tackled in case of nonlinear relationship, but to make the case simple, we are assuming that it is a linear relationship. So, these are x i's are low level requirements and these are high level requirement y's. That means, y is a function of x, or otherwise we can say y is a dependent parameter and x i's are independent parameter. Y depends on x, x does not depend upon y. Now, with this, if I use the that examples fabric stack, where we have seen there are 10 fabrics stacked together, the same example we are coming back. Nominal thickness is 0.2, tolerance is 0.02 mm and the process capability, let us say, is 1.33, which is a very good process. If Cp is 1.33, that means most of the fabrics which are produced will be meeting this requirement. Only very few, that percentage has been given earlier, it will be equivalent to almost 4 sigma level, and therefore, very few percentage of fabrics will be defective. So, thickness of the fabric stack is a linear function. Required target value of the fabric stack y is going to be 2 mm and delta 0 is going to be 0.2 mm. So, required Cp, suppose I need 2, which is a very high value. So, suppose I, as example I take it 2, is the process capable enough to meet the specifications or not? If that is the question that is raised. So, these are the requirements given, and this is what the fabrics that we will use it to make a stack. So, fabric manufacturing process has a capability of Cp 1.33 and the stack should have a give me a thickness of 2 mm and with a delta 0 value tolerance 0.2 mm, but Cp requirement is going to be 2. Is it attainable or not? Solution for this is going to be that since delta I is 3 Cp sigma I that we have seen, therefore, the standard deviation of the xi's is going to be delta I by 3 Cp. So, delta is 0.02 given already 3, Cp value of the process is 1.33, and therefore, the sigma value is going to be 0.005. The variability in y is A1 sigma squared, A2 sigma 2 square, like that. This formula we have stated, and if sigma is at all same, in this case 0.005, and how many of them are there? All A1s are basically 1, because y we have seen is x 1 plus x 2 by x 3, that means this constant A1, A2, A3 they are all 1. So, it is going to be 1 square into 0.005 square plus 1 square into 0.005 square, like that it will go up to n is going to be 10. Hence, this value is going to be 10 into 0.005 square. So, this value is going to be this value 0.000025. Therefore, sigma of y is going to be square root of this, which is going to be 0.0158. And Cp of y is therefore going to be, Cp is delta 0 by 3 sigma. So, in this case it is going to be 4.21. So, what we see here, the calculated Cp is much more than Cp requirement of 2. So, the process is capable to achieve this in this case. It will be able to meet the requirement. If let the tolerance of the fabric stack is reduced to 0.1 mm, in that case we will find that Cp is going to be 2.1. Even now Cp calculated is more than Cp required 2. So, it would still that if we reduce the tolerance. So, tolerance earlier was how much? 0.02 mm. This was the tolerance. If this tolerance is changed to even 0.1 mm, 0.1 mm. So, earlier it was very tight tolerance. No, this time if we increase it to 0.1 even, that means we have reduced. There the other example that we have chosen, where we have also given now the, so target values, all everything remains same, only what is extra here, the Cp value was not there earlier. So, we say the Cp is 1.33 for fabric A and B. C is A plus B plus Y, and in this case the requirement for this clearance is between 1 to 5 centimeter. So, solution if we go, process will be mostly similar. The target value of C, let us say T c, tolerance are delta dash C and delta C, y is between 1 and 5 already stated. So, the midpoint of the clearance is going to be 1 plus 5 by 2, that is 3, and E of y is going to be E of C minus E of B, expected value of B, expected value of A, this would be not B, this would be A, because we know that y is C minus B minus A. So, expected value of y, that is the middle point of y, is going to be how much? 5 plus 1 by 2, that is 3. So, 3 is going to be T c minus 20 minus 10, T t, the nominal value of B is 20, the nominal value of A, and so B is I think 10. So, this is actually I think nominal value was 10, this was 20. So, it will be 20 minus 10, or I think it could be 10 minus 20, whatever, basically minus 20 minus 10 both will come here. and therefore, the target value of C is going to be T C is going to be 20 plus 10 plus 3, that is 33. That is, C target value has to be, or nominal value has to be 33. The units are same, centimeter. We can should be like this. If we rewrite it now, okay, from there we go to the next page now. So, we have found out the target value of the packet, that is C. Now, we still need to know what should be the tolerance. That calculation is still left. So, C p has been stated to be 1.33 for the process which are folding the fabrics and making it 20 centimeter and 10 centimeter for fabric A and B. So, in that process also the nominal value is 20 or 10, but the process capability is that C p value 1.33. That means, sometimes we get it 20 plus something, 20 minus something. So, what is the standard deviation of that process? Suppose folding of fabric is done by some machine, it is done automatically by some machine, and that machine, folding machine, is having a process capability of 1.33. So, delta A is delta, so sigma A is going to be delta A by 3 C p. So, if we go by this tolerance has been given to be 1 stated, it has been given 3 into C p value 1.33 is, therefore, I find out that the standard deviation of A is going to be 0.25, and therefore, similarly standard deviation of B is also going to be 0.25, because the tolerance of B is also same like tolerance of A, both are plus minus 1 centimeter. Now, variance of clearance y is going to be how much? Y is a function of A, B, C, and therefore, variance of y is going to be sigma square A plus sigma square B plus sigma square C, that is equal to sigma A we already know, sigma B we already know, both are 0.25, it will be going to be 2 into 0.25 whole square plus sigma square C. Sigma square C is something which we still do not know. What is the standard deviation for the dimension of the packet, which is still unknown to us, but for the y the required C p has to be 2. If it is 2, then the standard deviation required of that process will be how much? Again we use similar formula, sigma is going to be delta 0 by 3 C p. Delta 0 has been given to be 2, because it is a summation of delta 1 and delta 2, or delta A plus delta B, which is going to be 1 plus 1, that is going to be 2, and therefore, 3 C p, 3 into C p taken as 2, this value is going to be 0.33. Now, if sigma for the packet, that is C, is 0.33, how much is sigma square? 0.33 square, that is going to be 0.1089. Sigma square A as sigma square B is going to already seen, 2 into 0.25 whole squared, it will give you a figure 0.125. Now, therefore, what happens is that this sigma squared is not going to be sigma A square, sigma B square plus sigma C square. This sigma square is less than current sigma square A plus sigma square B, and therefore, there will be no feasible sigma C and delta C unless the tolerance of A and B are changed. we are not getting a solution, because in one side we want this should be satisfied, and if the value of sigma variance of y, this is basically not y, this is the variance of y. So, this will be sigma square y. If that value is 0.1089 and the right hand side, if summation of these two is 0.125, then sigma square c has to be then negative. The variance cannot be negative, and therefore, it will not give you any feasible solution, there is not possible. So, what we need, that we need to change the tolerance of A and B, that is these tolerances of A, that is delta A and delta B has to be changed, otherwise it is not going to give you any solution. So, let us assume that delta A, sigma B, sigma C are all same, because sigma C was coming negative in the previous case. Now, let us say that they are all same, the variability in A, B and also C in terms of standard deviations are same. Therefore, sigma square is going to be 3 sigma A square, and they are all equal to 0.33 square, and this will be how much? A minute. No, sigma square we have found out to be already 0.1089. If they are all same, then this is equivalent to 3 sigma square. So, 3 sigma square is 0.1089, and therefore, sigma A has to be how much? 0.19, and same is going to be the sigma B and sigma C, all of them is going to be same. So, that means sigma A is 0.19, sigma E is also going to be 0.19 and sigma C also going to be 0.19. So, how do we arrive it here? Now, we are assuming that to be same. Sigma square is the already we have found out in the previous slide, that is 0.10189. So, 0.1089 is equal to 3 sigma A square, and sigma A we find it out, and that same thing becomes sigma B, and that becomes sigma C also. If the Cp is still 1.33 for A, B and C, then delta A, delta B, delta C is 3 Cp sigma A, that is 3 into 1.33, 0.19, that is 0.758. So, these are the tolerances for A, B and C. So, one is the tolerance, the other one is the standard deviations. From there, now we can verify whether results are coming correct or not. The clearance in the present case, in the worst case, after assuming that the sigma A, sigma B, sigma C are same, T C we have already found out. Target value of C already we have found out, that is T C equal to 33. Considering the smallest size of A and B, how much is going to be the clearance Y? T C minus 0.76, minus 10, 10 minus 1, that is going to be 32.24 minus 19 minus 9, 4.24. Considering the biggest size of A and B, Y is going to be T C plus 0.76 minus 20 plus 1 minus 10 plus 1. So, this is be 32.24 minus 19 minus 9, this will give you a value 4.24. That is, the clearance of Y in the one worst case is 4.24. In the other worst case, we are assuming the biggest size of A and B. So, we are assuming 20 plus 1, 10 plus 1, 33.76 minus 21 minus 11, that gives you a figure 1.76. What was the requirement? Requirement was y should be between 1 and 5. So, in this case, you see the worst case scenario, the y value in one case may come 4.24 or it can come 1.76. So, it is greater than 1, but less than 5. So, it is then fulfilled. So, the requirement is now fulfilled. So, with this we close this particular discussion, which is on tolerance design. So, in many in the tolerance design, in some cases where the textile products will be will have some critical use, especially there it will be very important. In many cases it may not be that important, because we can have wide tolerances also, because it is not a life threatening product, but there could be some products where it could be have an implication on the life of a person. In those situations, meeting tolerances or designing as per tolerances becomes extremely important. Okay. With this, let us close today's session. Thank you.